Okay, hello everyone. Today we are going to discuss about the lattice structure of Rocksalt.
So before we start our presentations, let's introduce ourselves first. My name is Simen Z.
And I am Afiq Ashraf.
You wake up in the morning and you plan to make breakfast for yourself. You make egg and bacon for your breakfast, season it with salt alone. However, did you ever wonder about the appearance and structure of the salt? Let's address your curiosity and have a detailed look into the salt structure. This is the structure of a salt. You may see that the structure of a salt is formed by small brown particles that are bound to each other in an arranged order. That's why we call it crystal. A crystal is a substance that contains component atoms arranged in a defined pattern. To be more specific, the structure of the salt is rock salt. Before I go into detail about the structure, you may need to know that salt is an ionic compound that is formed by sodium cation and chloride anion. Ionic compounds are formed from the attraction between an ion and cation with different charges through electrostatic force. Okay, so basically, the larger ion will form the frame of the structure. The electronic configuration of a sodium ion is 1s2, 2s2, 2p6, while the electronic configuration of chloride ion is 1s2, 2s2, 2p6, 3s2, 3p6. The chloride ion has a higher energy level and more electron shelf than the sodium ion. Hence, the chloride ion is larger than the sodium ion. Therefore, it will form the frame of the structure. Let's ignore the sodium ions and just look at the frame ion of the chloride ions. The unit cell of a chloride ion is a phase central cubic, which belongs to the brevis lattice for the crystal system of cubics. Oh, by the way, unit cell is the smallest repeating unit of a full crystal symmetry. In other words, the salt structure formed by many phase central cubic. Next, the lattice parameter include the length, width, and height, all of which are equal, which the angle between the cubic alpha, beta, and gamma are all 90 degrees. Additionally, the phase central cubic structure is one of the closed packed structure, where the arrangement of the atoms is in a way of high packing efficiency. Let me illustrate this with a model. If you arrange one layer of atom directly on top of another layer, there will be a large vacant space in the middle. However, if you arrange the layer of the atom so that they are staggered, the spacing in the structure will be reduced, leaving less vacant space and creating a more stable structure. The same principle applies to the theory of closed-packed structure of rock salt. For your information, tetrahedral and octahedral are geometry with high symmetry point groups. A tetrahedral geometry consists of 4 atoms bonded to a central atom, with the atoms separated by equal angles of 109.5 degrees. An octahedral geometry consists of 6 atoms bonded to a central atom, with the atoms separated by equal angles of 90 degrees. It resembles a stick passing through a square piece of paper at a right angle. You can find tetrahedral and octahedral void inclusive packed structures such as phase central cubic (FCC) and hexagonal closed packed (HCP) structures. In these structures, the central atom of the octahedral and tetrahedral void represent a vacant space, and the surrounding atoms are part of a framework. Additionally, not all lattice FCC and HCP both have filled tetrahedral or octahedral void. As we discuss the rock salt structure, let's focus on it specifically. In rock salt, the octahedral void are fully filled, while the tetrahedral void are completely empty. Now we add the sodium ions. Sodium ions are located between all the chloride ions in the octahedral void of the phase central cubic structure. An octahedral void is a vacant site in the phase central cubic structure that is bound and surrounded by 6 framework atoms. The octahedral shape can be observed through the bonding between the framework atoms and the void space. Hence, we can deduce the 6 chloride ions will be bound to 1 sodium ion. Additionally, 6 sodium ions will also be bound to 1 chloride ion. Therefore, we can conclude that the coordination number of sodium chloride is 6. In addition to the octahedral void, there are also tetrahedral void in the phase central cubic FCC structure. However, in the case of sodium chloride, this tetrahedral void remain unoccupied. Thus, tetrahedral void do not play a significant role in the sodium chloride structure. Each unit cell of FCC structure contains 8 tetrahedral void. You can divide one unit cell into 8 equal size cubes, each with a tetrahedral void in the center. But the presence of tetrahedral void might not be significant. Let me magnify and isolate the tetrahedral structure for you. Here it is. This is tetrahedral structure. By examining it closely, you can see how the tetrahedral void are positioned within the FCC structure lattice. For a more comprehensive understanding, I recommend rotating the structure. This will allow you to observe the most common general appearance of the tetrahedral void.
In the crystal structure of sodium chloride, the arrangement of ions is mostly highly organized and symmetrical. So, let's dive deeper into this configuration. First, Consider the FCC lattice formed by the chloride ions. In this lattice, chloride ions are positioned at the corners and the face center of the cubes. This creates a highly stable and symmetrical structure that forms the backbone of the crystal. There are 8 corner sites in a cubic unit cell, one at each corner of the cubes. Each corner site is shared by 8 adjacent unit cells. Consequently, each corner site contributes 1/8 of an ion to the unit cell. Since there are 8 corner sites and each contribute 1/8 to the unit formula, the number of ions located at the corner sites of the CCP frame structure is 1. There are 6 face sites in a cubic unit cell, one of each face of the cubes. Each face site is shared between 2 adjacent unit cells. Therefore, each face site contributes 1/2 of an ion to the unit cell. Since there are 6 face sites and each contribute 1/2 to the unit formula, by multiplying 6 by 1/2, we find that the number of ions located at the face sites of the CCP frame structure is 3. As mentioned, chloride ions form the framework structure in rock salt. Therefore, the total number of chloride ions per unit cell is the sum of the ions at the corner sites and the ions at the face sites. Thus, 3 plus 1 equals 4. Hence, the unit formula for chloride ion is 4. Now, within this FCC lattice of chloride ions, there are spaces known as octahedral voids. These voids are significant because they provide the locations where the sodium ion resides. There is one key octahedral void located at the right center of the unit cell. This central octahedral void is fully occupied by sodium ions, contributing 1 complete sodium ion to the unit cell. Furthermore, there are additional octahedral voids located at the cube's 12 edges. Each of these edge-center octahedral voids is shared among 4 adjacent unit cells. Due to this sharing, each edge-center octahedral voids contribute only 1/4 of a sodium ion to a single unit cell. To quantify this, we can calculate the total contribution of these edge-center octahedral voids. Since there are 12 edges in the cube and each edges contributes 1/4 of an ion, the combined contribution is effectively 3 sodium ions per unit cell. Adding this to the 1 central sodium ion, we get a total of 4 sodium ions per unit cell. Thus, the sodium chloride unit cell adopting a face center cubic structure contain a total of 4 ions and 4 anions. Don't get me wrong, the total number of ions in one unit cell of sodium chloride in rock salt is 8. However, the unit formula for rock salt will be 4 instead of 8. It is because one molecule of sodium chloride is formed from 1 sodium ion bonded to 1 chloride ion. This configuration ensures that sodium ions fully fill the octahedral voids within the FCC lattice of chloride ion efficiently and symmetrically. Rock salt or sodium chloride has numerous applications across various industry and everyday life. So, let's begin with the food industry. Rock salt is a staple in food preparation. It is widely used as a seasoning to enhance flavor in countless dishes. Additionally, it acts as preservative, helping to extend the shelf life of various foods by inhibiting the growth of bacteria. Beyond just flavor and preservation, rock salt is a crucial ingredient in many recipes, providing essential sodium for our diets. Now, moving on to water treatment. Rock salt plays a vital role in ensuring clean and safe drinking water. It is used in water treatment processes to remove impurities and soften water. The process of ion exchange facilitated by rock salts help to reduce the hardness of water, which can cause scaling in pipes and reduce the effectiveness of soap. Furthermore, rock salt is used in disinfecting water supplies, making it safe for consumption by eliminating harmful microorganisms. So now, let's look at the health and beauty sector. Rocksalt is incorporated into a variety of spa treatments, bath salts, and skincare products. Its natural exfoliating properties help to remove dead skin cells, leaving the skin smooth and rejuvenated. Additionally, the purifying properties of rock salt make it an excellent ingredient for detoxifying treatments, promoting overall skin health and relaxation. And lastly, rock salt also has significant application in animal husbandry. It is used in agricultural practices to provide essential mineral to livestock. Animals require sodium for proper growth, nerve function, and muscle contraction. Rock salt is often included in animal feed as a supplement to ensure they receive adequate sodium. Moreover, it helps in improving the overall health and productivity of the livestock. So, in conclusion, rock salt is an incredibly versatile substance with application spanning from enhancing food flavor and preserving safety to promoting health and supporting agriculture. Its widespread use underscores its importance in our everyday life and various industrial processes.